Hi folks, welcome back to Physics with Captain Rod. Making this as a follow-up to the problem we looked at the other day in class here. So this half disk here rotating back and forth. So some important points about this problem. This distance to the center of mass is going to be very important, and that is easily looked up. That's 4r over 3 pi. I got 0.112 feet when I did that. This distance here, which I've called r bar here for the rest of the problem, is probably going to be important. I calculated that at 0.388 feet. The moment of inertia of this system about the instantaneous center is going to be important. And what I'm going to do for the kinetic energy term is just approximate it as rotating about this point. And therefore what we need is the moment of inertia of this object here about this axis. So when we do that, let's see, we can get that by starting with the moment of inertia of an entire disk, which I know is 1/2 mr squared. And therefore the moment of inertia of this half disk about that green dot would be 1/4 mr squared. By the parallel axis theorem, the moment of inertia of this system about this dot has to equal the moment of inertia about g plus an md squared term, where again the d is 0.112 feet. So that's how I calculated the moment of inertia about g. I got 0.0156 slug foot squared for the moment of inertia about g. To get the moment of inertia about the instantaneous center of rotation, I just tacked on an mr squared term. And again, I'm approximating it as rotation about this point, which is a reasonable approximation if we're talking about small thetas here. And I got 0.063 slug foot squared for this problem. All right, so now the first step here, and I've already done it, is to write out something for the total mechanical energy of the system. So I'll just work this backwards. So the energy of the system is equal to its kinetic energy, which is 1/2 I theta dot squared, approximating it as rotation about this point using this value for I. Then the potential energy term. So I went ahead and finally got this to work out right with my plus and minuses here by, again, leaving a datum at the ground here and see if I can remember what I did. First of all, let's talk about this distance right here. So this displacement here is an angle theta. That makes this distance along here approximately r bar times theta. And from this triangle, I'm sorry, did I say approximately? That's exactly r bar times theta. And then from this triangle here, here's an angle theta. This height is opposite theta. So that height would be equal or approximately equal to r bar theta gives the hypotenuse times sine theta gives that height. So that's that term right here. And then from here to here is equal to r bar cosine theta. So the sum of these two gives the total height of this system above my datum, height of the center of mass. So the potential energy term looks like this: mg r bar cosine theta plus r bar theta sine theta. Okay, I'm going to let you folks work through the differentiation, but I did that. And these two terms ended up adding to 0, and I got this for my differential equation here. Solving it, highest derivative first with a 1 in front of it, put in numerical values. When I put in numerical values for everything we have right here, I got 62 out of that. And again, I'm not going through this in great detail here, but a standard assumption of theta equals a sine omega t subbed into this equation, you should get an omega of root 62 out of that. And then I got 7.8 radian per second. And then remember that your angular frequency is 2 pi times this frequency. So dividing that by 2 pi, I got a frequency of about 1.25 hertz. Now, there could be a numerical mistake somewhere in here, but I stand by the method. I think it's reasonable. And again, this was approximating the kinetic energy as rotation about this point. But as long as we're talking about small displacements, that should be pretty good. So hope this video helps. Have a great day.